All right, exponential population model. Okay, if the population, we'll call that P for population, is changing at a constant percentage rate, and we'll call that rate R, P for population, R for rate, then we come up with an equation that looks a little bit like this. Okay, the population, okay, with respect to time, T, equals P sub 0 times 1 plus or minus R raised to T, which is time, okay? Now, we've seen this before, kind of represented differently, okay? And note down here, P sub 0 or P sub O or poo, this is your initial population, which you can think of as an initial value. Didn't we just see initial value last class? That was the A, right? Then A, B to the X. Okay? It's the initial population. R is expressed as a decimal. Okay? Meaning, if they give you a percentage rate for 25%, R needs to be in decimal. How do I make that in a decimal? I divide by 100, or if the decimal's here, I slide it over twice. 0.25 is 25%. Yeah. So R needs to be in a decimal, because when we use a calculator, there's no percent key in the calculator. We just need to make it in a decimal. And T is typically time in years for population. Okay? So, it should look familiar right now. We just did the exponential function a b to the x. Well, if p to the if p sub 0 is our initial value, well, that's pretty much just like a. Okay? And t is time in years. That's our exponent. That's our variable. Okay? That's our variable x, which leaves us with one variable in our exponential function left, b. Okay? So that has to be here. This is like our b value. So really, we have a times b raised to the x still. We still have it. But there's a little quick note down here, because yesterday when we were talking about exponentials, it can grow or decay, right? Increase or decrease. If your R value is greater than 0, then P of T is an exponential growth function. And its growth factor, remember B was a factor, if B was a 2, it was like 200%, right? It would double. Okay? But our growth factor B is 1 plus R. If it's growing, wouldn't it make sense that we need to add our rate to 1? 1 stands for 100%. Well, if it's growing, it's going to grow to more. It's going to grow over 100%. So we add whatever our R value is. That represents growth. Adding the R. So I think you guys can pretty much predict what happens next. If our rate percentage, our 0.25, whatever it is less than 0, it's negative, well, then it's decay. Because our decay factor will just be, it's 1 minus R. Okay? It's 1 minus R. All right? So whether you see a plus or minus here, it's going to tell you, right here, whether it's growing or decaying. All right? Sometimes they add it for you and you got to kind of like figure it out on your own. But it's really not that difficult. It's really not that difficult. So you just compare it to the number 1. Is it bigger than 1? Yeah, then I probably added something to it, so it's growing. Is my value less than 1? Well, then you probably subtracted something to it, so it's decaying. Right? Not rocket science. Yes. All right. So example 1 here says, tell whether the population model is growing or decaying, and find the constant percentage rate for the growth or decay. Okay, we don't have to figure out the population of San Jose after like 10 years or anything. When I look at this first one, I just want you to tell me, do you think the population of San Jose is growing or shrinking? Is it growing or decaying? What do you think? It's growing. How come? It's This right here, this is our growth factor. That's our b, right? That's 1 plus r should equal 1.0136. So what do you think I had to add? Well, let me put it this way first. The reason I know it's growing is, what do you think I had to add something to 1 or subtract something to 1 to get this value? I had to add. It's bigger than 1. There's no way. I can't subtract anything from 1 and make it greater than 1. That's nearly impossible. Unless you subtract a negative, which is like adding, which is just bigger than 1. Okay? Yeah. So now, what do you think my R value is here? What do you think I added to 1? Yeah. I added, that's 1 plus 0.0136. That's my decimal. They just want a percentage. So how do I turn that into a percentage? Yeah, I'll slide the decimal over 2 to the right instead of to the left. So when I slide this 2 to the right, 1.36%. So guess what? San Jose is growing at a rate of 1.36%. That's it. That's it. I'll give you guys a minute. Let me see if you can figure out whether Detroit is growing or decaying and what that rate is. All right, Detroit. First of all, growth, decay? Decay. Why do you think it's decay? It's less than 1. I had to subtract a value from 1 to get this right here. I had to. Okay? So I want to subtract R should equal my 0.9858. Okay, so now I can solve for R. How do I solve for R there? Well, it's simple. Why don't you tell me what R is instead of telling me how to solve for it? So R equals 0.0142. And how do we do that? Simple algebra. Okay, just you can subtract 1 from both sides, and you get negative R equals negative 0.0142. And I just divide both sides by negative. We want R. We don't want negative R's. R should be a negative value. 1 minus this will give me this right here. Okay? Now, change that to percent. What is it? Yeah, slide the decimal over twice. 1 and 2 right there. 1.42%. Okay, so the first one was a growth. Second one is a decay. All right, and I think it's fairly easy to tell it's above 1 here for San Jose. So it's a growth. It's below 1 for Detroit, so it's decay. Now, sometimes they're nice. For example, for Detroit here, instead of writing it like that, they might in the front say 1 minus 0.0142. And if that's the case, that's 1 minus the R. That's still decay. All right? That's easier to tell because you actually subtract. All right? What about Rochester? I think Rochester is growing about the way it's decaying. Decay. I think it is decay. And what we're going to do this, and you guys have your calculators, right? Let's actually do something. I looked up some values for Rochester. And we'll come back to these 3 questions in a second. This is the value of Rochester. I actually got this from, I got this information online on Wikipedia. Don't judge me. I don't know if it's Wikipedia or not. But when I first did this, I grabbed the population of Rochester in 1980, 1990, 2000, 2010. And you can tell just by looking at it, is it decreasing or is it increasing? Yeah, the number's going down, it's decreasing. So when we put together an equation for this, in parentheses, do you think that number is going to be less than 1 or more than 1? It's going to be less than 1, okay? This isn't rocket science. So let's go to our calculators, stat edit, enter this information, and I'm going to give you a hint to make your life a lot easier so the numbers will be small. Oh, you know what? I'm wondering if I did this with small numbers. Yes, I did. And we're going to do this. We're going to put these numbers in just from 1980 to 2010. But let's start 1980 is year 0. This would be 10, because it's 10 years after 1980. This will be 20, and this will be 30, okay? Otherwise, when you start putting 1980, our equation's going to be a lot bigger than it has to be. Okay? So I'm going to go to stats X, choice 1. And for the first column, I'm going to put in 0, because that's where I'm going to start with, 1980. Okay. 10 years for 1990, 20 for 2000, and 30 for 2010. Now, what were my values here? Because I can't see them. It was 241. They're on your notes, because they should be right in front of you. Oh, they're not. Dinky. 741. Good for you. Good for you. You told me. 741. The next one is 231, 636. The next one is 219, 773. 210, 565. All right? And the last one would be 210, 358. 210, 358. Did I? Yeah. Where there's a boo-boo. Where is it? What was 20? 0, 10, 20, 30. All I have to do is put in this one right here. 210, 565. Okay? There we go. Now, how do I create an equation from this information? How do I get my equation once I put my data in? Stat, calc, and what do I want to calculate? Any one of these? Yeah, aren't these exponentials? Exponential regression. It's an exponential regression. Our variable is the exponent. So I hit enter, and let's not forget, let's put this into y1. So when we look at our table, we don't got to retype the whole equation in. Okay? Anyone remember how to get y1? Bars. Y bars, I hit enter twice. Okay. Good. I'm going to calculate it. There you go. That's what it should be. So, for the time being, ooh, interesting. I'm going to put this right here. So that's what you should have in your calculator, all right? Now, this is different because the other class might have actually used this one. We're not. We're not going to use this. Okay? We're going to estimate what the year 2013 would be. Okay? This was based on a previous class. All right? So our y value isn't 241, 468. It's 984. Okay? And that's what we're going to use here. So this is inaccurate based on our information. Okay? Now, no, is that the exact same? Shouldn't year 0 start? Should the initial value always be right here? Shouldn't this be the initial value? But it's not, is it? That's because this is a line of best fits. It's going to be as close as possible. You know, it won't be exact sometimes, but it won't be exact other times. Because population won't always change according to a smooth line. You know? Sometimes it juts up, sometimes it juts up, sometimes it juts down, but it isn't always the same. Now, how can we tell what it's going to be for the year 2013? Let's go back to our calculator. If I go to y1, beautiful, this is all into our y1. Where do I go? Where should I look to find the values? The table. The table. Oh, you guys are crazy. So let's see how close our line of best fit is. After 10 years, it's 230, 949. It's only off by 500 people, 600 people. That's not too bad. It's not too bad considering that's almost 250,000 people. It's not bad. What about 20 years? So after 20 years, yeah. After 20 years, we should be at 219, 773. So let's go down to 20. So 220, 416. 220, I mean, that's about 600-700 people. That's not bad either. So now, what about the year 2013? Where do I need to go? What number? Well, if this is year 30, 2010, then this should be year 33, absolutely. And the great thing is, I get this table. I want to know, 50 years from now, I look at 50. I want to look at 100 years from now, I look at 100. Okay? So let's look at 33 and see what the population... Actually, this is 2015, right? Let's look at the population for 2015. So what would I go to? 35. 205,511. 205,511. Not too bad. All right, let's look at these questions here. They really don't have anything to do with math. Just, what do you think Rochester's population model, well, do you think it's growing or decaying? You guys told me before we even started, you guys think it was decaying. Okay? Why do you think it's decaying? Weather. Maybe no one wants to be here because of the weather. What else? What? Crime. What else? If you're an adult and you move here, what do you got to find? Jobs. Jobs. There needs to be jobs, right? Well, that new company's moving in. I forget what it's called. Some tech lab place. Yeah, and it's supposed to bring a lot of jobs, so people might come in, so the population might grow. All right, well, why do you think San Jose's population is growing and Detroit's is shrinking? Okay, they travel. It would take them further to travel to Detroit. Is that what you're saying? Than San Jose? Okay. Does anyone know what San Jose has over there? That's where Silicon Valley is. No, that's where they have Silicon Valley, where all the tech companies are, and there's always jobs there. There's always jobs there. Detroit, that's the car industry. You know how it went down. It's actually making a rebound. But Detroit's where the car companies were next. They were going down real bad. Okay, so the biggest driver of population growth? Employment, jobs. If there are companies that need people, they will try and get them in. If there is a place that has no jobs for people, people are going to leave to go find jobs. Okay? Other exponential growth and decay models. Okay? Population growth and decay models are used to represent populations of animals, bacteria, radioactive atoms. Okay? Exponential growth models can be built in terms of the time it takes to double the quantity or the time it takes to half the quantity. Like a science in terms of half-life.
Yeah. Radioactivity.
Yeah, there you go. Okay. Bacteria growth. And again, we can use our calculator to solve this, okay? Suppose a culture of 100 bacteria is put into a petri dish, and the culture doubles every hour, okay? Predict when the number of bacteria will reach 350,000. All right? So they got this function here. They're going to call it B of T. B is for bacteria, T is time. How do you think that's going to look? What's it going to start with? 100. Isn't that our initial value? That's our A value, 100. Okay? Times something. Now we know it's to the T. Okay? What do you think goes there? Something's got to go there. The rate.
It's got to be going up.
It's got to be going up, doesn't it? It's got to be going up. What's it increasing at? What's that? It doubles. It doubles. So guess what? If it doubles, 2 doubles. 1 plus 1, right? 100%. And if it doubles, you got to add another 100% to it. So 1 plus 2. Okay. So if this is our equation, they want to know when the bacteria is going to be 350,000. If this is our bacteria, they want to know when that's going to hit 350,000. I'm going to use a calculator to figure that out. Well, yes, we're not there yet. We're not there yet. Okay? Let's just do this. Why don't I put 100 times 2 to the x? And I want to just figure out what when I look at my table. Yeah, 350,000. I better go way up because we're down here. And what is t? It's time in what? T is time in what, according to the problem? Hours. It's time in hours. So, okay, at 0 hours, okay, and 0 hours, we're at 100. That's good. It's our initial value. After the first hour, doesn't it double? 200. It doubles after that. The next hour, 400. It keeps on going up. I got to find where I'm at 350,000. What is that? Is that, no, is that, that's million. Wow, that's up there. Between 11 and 12. Between 11 and 12 hours. That's when it's going to hit 350,000. All right? If you wanted to get exact, you have to see, if you want to get exact, I would have to graph this in Y1 and this in Y2 and see where they cross. Okay? But according to the table, if we did this right, according to the table, bam, when will they predict when the number of bacteria will reach 350,000? That is between 11 and 12 hours. Okay? Let's try to get exact here. Let's get a little nutty. I want to see when it equals 350,000. Okay? Which means, what do I need to do if I want to see where they cross? I got to change the window. I got to go all the way up to 350,000. On the Y. That's crazy. We know it's between 11 and 12, right, on the X. So let's go to our window. Let's go, for the X, we'll go from 10 to 13, right? This is between 11 and 12. Go by ones. And Y, it's around 350,000, right? So let's go from 300,000 to 400,000. And let's change the 100,000. 100, 1, 2, 3. There you go, that's where they cross. So how do I find the intersection point? Seconds. We don't want to trace. We want to calculate. Calculate the actual intersection. 5. Where are we? Oh my God. There we are. I hit enter, 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 enter. 11.77 we'll call it. You see that right here? 11.77. Boom. So there's approximately 11.77 hours. Okay. Example 3. Suppose the half-life of a certain radioactive substance, let's call it Viscanium, is 20 days. Okay? And there are 5 grams present initially. Find the time when there will be 1 gram of substance left. All right, well, let's come up with our equation. V of t equals what? 5, because that's what we start with. 5 grams initially, that's what we start with. Times something to the t. T represents increments of 20 days. Well, what's the increase or decrease? Is that a growth or decay?
Okay.
Decay. Because what? How do you know it's decay?
Because it has to compile.
Okay, yeah, I'll give you that. But what's my factor? It goes down in increments of what? Half-life. Which means it should be smaller than 1, right? Half. You lose a half every 20 days. That's what half-life stands for. You lose a half every 20 days. So I want to figure out when this equals what? When there's going to be 1 gram left. So I'll set this equal to 1. I'll put this into Y1 and this into Y2, and I'll get an answer for T. That's all. Oh, I'm definitely going to change the window. We can't be at 350,000 anymore. So, for Y1, clear that. It is 5 times, well, 1/2 is the same thing as 0.5 to the X. This is going to be 1. clear one. And let's go to a standard window. 10 by 10. Okay. Alright, well, there's the first thing. There's one. Okay, it intersects. It intersects somewhere, I don't know, about here. So I need to use the intersection function again. Second, calculate the intersection. Come down there closer to the thing. Hit enter once, and enter twice, and enter third times. Okay, 2.32. Now, is that what it is? Is it 2.32 days?
No.
No, it is not. 2 is approximately 2.32. But how many days is that?
It's like 40 something.
Yeah, because doesn't T represent 20-day increments? This is how, if I had 2 20-day increments, it would be 40. Because I'm multiplying, don't I? So this is T is in 20 days. That equals 1T. So I got to multiply 20 times 2.32. What is that in your calculator? 20 times 2.32. 46.4, approximately. So it will take approximately 46.4 what? Days. It'll take 46.4 days to get from 5 grams to 1 gram. Okay, this last problem, for the sake of time, we're going to forego. We're not going to do it. But this is the same thing we would have done for Rochester, right? Under L1 or LS stat edit, these go under L2 stat edit. And then you want a stat calc, and we want the exponential regression, because these are exponentials. And that will give you the actual equation. Okay? There's one problem on your homework like that. The rest are calculating like we just did. Okay? One problem on your homework that is like this. We'll see how you guys do. Bring it in tomorrow and we'll go over some stuff.